about the wave equation. So this is the wave equation, and then we have these two boundary conditions, Dirichlet and Newman boundaries. And so the Newman boundary, you see, that's the free surface boundary, where we impose that the derivatives of S are equal to 0. This is a stress-free boundary. That's what we impose for the free surface, for example. And then on the left, you see the Dirichlet boundary, where we just impose what the displacement is. So that's more like the string of a guitar, where we fix the endpoint and then see how a wave would travel along that string. So we use this initial displacement and then just let it go. So what we solve is the homogeneous wave equation. There's no additional force term. So we can solve this with the homogeneous wave equation, then we put this into the weak form. And you see the last term here of the weak form, that's the boundary term. So we do have to keep to compute that boundary term for the very last point at L, the very first point at 0, where we have the boundary. Now, if we impose the Newman boundary, where the derivative of S is 0, then this boundary term just is 0 as well. So if you don't implement this boundary term, this is equivalent with imposing the Newman boundary. But if we have the Dirichlet boundary, we still have to keep track of that boundary term. We still have to compute that. And then impose the actual temperature value at the very last points, first and last points. Good. Here the matrix form would look like this. Again, we can do it matrix free, which means basically we don't need to store and assemble the full stiffness matrix anymore. We can just do this right-hand side version of it. And here, what is the right-hand side? So it basically means that if we want to compute what the acceleration is, if you look here in the matrix form, acceleration is this second order time derivative of S, would be 1 over m times the right-hand side times k times S. So when we compute that, we actually compute the acceleration. Good, this is the mapping. That's the same like in the previous homework. Interpolation is also the same. These are quadrature rules and Lagrange polynomials. So the setup keeps being the same actually between the previous example and this example. The mass matrix looks a little bit different. We don't have a specific heat here, just have density. And for the stiffness matrix, we have the shear modulus rather than having the conductivity kappa. But again, the rest is all the same. So mass matrix and stiffness matrix, the local contributions look almost identical to what we have in the previous example. The boundary terms, again, here it's just with the shear modulus instead of the kappa as a material property. Otherwise, the terms are again the same. The global index, that's also the same like in the previous example, and so the assembly basically is also the same, the steps that we have. So only this, you see it on top, the local contribution for the mass matrix slightly different because we only have density in this case, not the specific heat anymore. Good, and then the time stepping. So what we use is this so-called Newmark algorithm for the time stepping. And now let me put down a quick note on this time stepping scheme that we use for the wave equation. So I'll stop here. And then try and connect with the whiteboard. Right, so you see the notes now? Good. So what I want to put down is just a few notes for this time marching scheme, this Newmark algorithm that we are using for the wave equation implementation. So let me quickly put that down. So for the wave equation, we employ, so-called Newmark scheme. Which belongs to the family of the predictor corrector schemes. So the Newmark scheme so it keeps track of displacement, that's d, and at time tn, so that's dn. We have velocity that we need, which we call Vn for time step Tn, and also acceleration. Which we call An. So in matrix form, we can simply write that the mass matrix times the acceleration equals to the force on the right-hand side vector. And so in order to solve for the acceleration at time n plus 1, we simply divide by the mass matrix. So we have 1 over m times the force vector, or the right-hand side vector, times n plus 1. So the question then is, what is this force right-hand side vector? But for stepping this, so let's look at the scheme in order now to use the time stepping. So the stepping uses the following updates. So we have the displacement update, which uses the previous displacement plus the time step size times the velocity plus this time step size squared of 1/2 minus beta times the velocity at the acceleration at time n plus beta times the acceleration at time n plus 1. And velocity plus 1. So we come to this beta factor in a second. Let's quickly write down the velocity update. So velocity update will be using the velocity from the previous step plus the time step size times 1 minus gamma times the acceleration at time n plus gamma, acceleration at n plus 1. So this will be the general Newmark scheme, where we have these beta and gamma parameters. So involving parameters beta and gamma. And these parameters are something that we can choose what the values should be for these parameters. So if we look at these step updates for displacement and velocity, you see, for example, that if we choose factor beta and gamma bigger than 1/2, then we do have implicit updates. So then we have these contributions from the acceleration at n plus 1. So the scheme becomes an implicit scheme, and the implicit time scheme is unconditionally stable. So for that choice, when we choose beta and gamma bigger than 1/2, we have an unconditionally stable scheme, which means we can choose the time step size as big as we want. So what if we choose gamma to be bigger than 1/2 and beta to be less than 1/2? Well, in that case, then the scheme can still be an implicit, but it becomes then only conditionally stable for such a choice. So there will be a time step size condition, how large we can choose the time step size. So we are no more free of just selecting a step size for delta t as we want it to be. But there will be a condition on that one. So also, what about the order of that scheme? Well, the scheme is second order accurate. But only if we choose gamma to be equal to 1/2. Good, that's something that we want actually. We want to have a second order at least scheme. So that will pretty much determine what we will choose for gamma to be. And then the second property of that scheme is that the angular momentum is conserved, but only if we choose beta to be 0 and gamma to be 1/2. So why is that important, angular momentum? Do we deal about angular momentum when we look at the wave equation?
Well, while deriving the wave equation, we conserved angular momentum, if I remember correctly.
Right, if you remember our conservation laws, angular momentum is conserved when we have this symmetric stress tensor. And it is something that we want to have when we look at the wave equation. So having a scheme which numerically is accurate in conserving the quantity, and that's an advantage of the scheme. So you see, if we want it to be conserved, which for the wave equation we very much want so, then that's giving us what the choice should be for beta and gamma. And you also see that the choice for gamma means that then the scheme also is second order accurate. So it's conserving angular momentum plus it's second order accurate for that choice that we're going to make. So at the end, it becomes like an obvious choice what we want to select for the wave equation. So we want to have beta equals to 0 and gamma equals to 1/2. So let's use that choice. So this leads to what then? So we have this predictor step. So at the very beginning of the time stepping, what we use is this prediction of the displacement step, where we use now our choice for beta. So if beta is 0, then we have here this factor 1/2 delta t square times the acceleration at time step n. Good. What's the update for velocity? So the predictor step will be the velocity plus, now gamma is 1/2. So we do have a term which involves the acceleration from the previous time step, but then we also need to compute the acceleration from the current time step, or n+1. So the predictor step is using this previous acceleration. So we have 1/2 delta t times an, acceleration from time step n. And then if you look at the scheme above, we still are missing then a term. We're still missing this term with 1/2 of acceleration at n+1. So that's the acceleration that we still have to solve for now. So at the very beginning, in the predictor step, we set this to 0, this acceleration field. for n+1. Then comes the actual solve for our degrees of freedom. So we have the mass times the corrector term for the acceleration is equal to Fn+1, which means that this corrector term for the acceleration is 1 over m times the right-hand side vector highlighted at n+1. And then comes the corrector step. And here we have now the correction step for acceleration would be the acceleration n+1 plus this acceleration corrector, delta A. The velocity uses our prediction for n+1 plus this additional term 1/2 delta t a n+1. And then the displacement, well, that's already the same like the prediction step. So there are two things to note. You see that the displacement at n+1 is already given by the predictor step. And so the right-hand side vector, Fn+1, for example, for that we need the displacement at the n+1. So we do have that already. So we can compute this explicitly, what then the corrected terms should be for the acceleration. And if you look at the acceleration field n+1, we start with 0 and then have the corrector step a n+1 is the previous from the predictor, which is 0, plus this corrected term for the acceleration. So again, what we actually solve in this corrector expression is already the acceleration at time n+1. And then in order to have all three fields, displacement, velocity, and acceleration at time n+1, we still need to update the velocity. That one is the only one with a missing corrected term, basically. So the scheme is fully explicit, it's second order, and theoretically already conserves angular momentum. So it's very well suited for the wave equation. Good. If you remember the difference to the heat equation, the main difference here is we have three fields that we keep track of: displacement, velocity, and acceleration. Where for the heat equation, you remember we had temperature and the derivative of the temperature field, T and T dot that we had. So now we have three fields, basically, for the wave equation. So it is related to the time derivative, to the order of the time derivative of the equation. In the heat equation, the time derivative was first order. Here we have second order for the time derivative, which increases the fields, basically. So if we increase the order, we increase the number of fields that we need in these schemes. Good. So this is the main points about the Newmark scheme that we use for the wave equation. There are some practical notes. Let me quickly tell you more about the stability from a practical point of view. So you see the choice that we have with beta 0 and gamma 1/2. It means we are in this conditionally stable regime of the scheme. So there's a time step condition involved for our choice for beta and gamma. And so from a practical point of view, the criterion, stability criterion that we have is that we need about 5 grid points per wavelength. Like to accurately resolve the given wavelength. And this, at least if we're talking about a fourth order scheme. Polynomials. Which means that the number of GLL points per element is equal to 5. So that means in principle the element size should be comparable to the minimum wavelength that we want to resolve. Because we will have 5 grid points per element and for a fourth order scheme. So if we fix what the minimum wavelength should be, that tells us more or less how large we can choose the element size. I've used these fourth order schemes. And then the stability condition, or the so-called Courant condition. For numerical stability, that's pretty much the same that we had figured out in our analysis about numerical stability. So is this one, that the wave speed c times the time step size divided by the grid spacing between the nodes should be less than 1. So this gives us a condition about how large we can choose the time step size once we have the grids set up and the wave speeds imposed for that simulation. So c would be the wave speed, which, for example, in our 1D example would be the shear moduli divided by density and the square root of it. And then delta x, that would be the grid node spacing. So if you remember, the grid node spacing for these GLL points is not equal. So grid nodes are spaced closer to each other when they are at the edges of the element. And they're a bit further apart in the middle of the element. And so here delta x is not quite clear which spacing do we take now. Do we take the minimum spacing? Or do we take an average spacing? So there is a bit of leeway in how we want to interpret that condition. But in principle, you would look at what's leading to the maximum stability, which means if we take delta t has then to be small or equal delta x divided by c. So if we take the minimum spacing at the maximum wave speed, that gives us the most strict condition for the time step size. So that's what we usually take then. So here we would take delta x minimum and c maximum to estimate time step size. But so there's a bit of ways to play around actually with this stability condition. And the condition is not a hard limit on the time step size. Doesn't mean that if we go a little bit beyond the condition with our time step size, that the scheme becomes unstable. It's not necessarily just becoming unstable, but what we see is it's not as accurate anymore. There's a little bit of a gray zone area where the scheme just starts deviating from the actual solution before it really blows up, before it really goes into this unstable regime. So yes, if we would like choose a long enough time, keep iterating our time step, at some point then yes, it will become unstable. But often we cut our simulation time just to a timing which is interesting for us. And within that time frame, it doesn't need to actually blow up yet, the scheme, even if we are beyond a little bit. But we see that the accuracy goes down, it drops basically. So this would mean for a maximum time step size. Right. One final remark is the time step size here. Once we set delta t, it's delta t everywhere in the scheme. It applies to all the elements. So it's a global time step scheme that we have. there are local time step schemes where the delta t can change from one element to another. Those would be called local time step schemes. They would involve a bit more sophistication, but it can be done. You can have local time step schemes also for the wave equation implementation. So then the time step size here, delta t, becomes a local time step size, local to each element, basically. Each element can have then its own time step size. But it makes it tricky to then basically compute the values at the corresponding timing between elements. So you need to make sure that the actual update then on the displacement field is done properly with all these different timings that you have. Good. So let me stop sharing here. The material for homework 8 you have on GitHub already. I put you the codes there. Again, it's Fortran codes or a Python version of it that you can start changing. And so the Python version is very close to what we had already. Let's quickly show you that. So this would be the Python template for now the wave equation. And it's, again, it's very similar to the previous example with the setup. Then here again, you would look at what now the mathematics contribution is, you do the assembly. And then figure out how this Newmark scheme, for example, would look like, etc. Good so far? Good. Then I would say we are done for today. Try and finish this homework 8 by next Sunday, again within a week. There's not much coding, or at least it's very similar to what you already had for homework 7. So look at the homework 8, try and implement by next Sunday, and then we can discuss it next Sunday. And so we meet again next Thursday, and then we just do the little quiz for next Thursday. That's it. Well, we basically look at these 4 methods that we had now. So with today's final remark about the Newmark time stepping scheme, we are basically done with all 4 schemes: finite difference, pseudospectral, finite element, and spectral element schemes. So there's no more theory to come about these schemes. So the quiz will be about these 4. Will be a multiple choice for you just to see if you understood it, and then we can discuss it next Thursday, go through this, and then see what we want to do for the final few lectures that we have. Okay? Okay with everyone? Nobody needs to go for a visa excursion next Thursday or something? Would be a pity if you miss it. No, good. Good, then let's do that. We see each other next Thursday again. Then I wish you.
Bye, thanks.
Stay home, stay safe. Well, sometimes you have to go out as well, right? Good. See you, everyone.
Thank you. Bye-bye.
Thank you, Professor.
Bye.
Bye.